Okay, so we're going to do number 8 from your worksheet. Oops. Let me go back here. We're going to start with lithium. So the noble gas before lithium is helium. So we're going to put helium in brackets. And then after helium is going to be 2s. And so helium represents 2 electrons, so lithium only has 3, so we only have 1 more left, and it's going to go into 2s1. And then for calcium, the noble gas before calcium is argon, so we're going to start with argon in brackets. Argon is 18 electrons, and then next would be 4s, and we only have 2 more electrons, so we're going to put those in 4s. Then vanadium, same thing, it has argon as the noble gas before vanadium. So we start with argon, and then we're going to go to 4s, put 2 electrons, so that represents a total of 20 electrons right there. And then we only have 3 more, so we're going to put it in 3d. Okay, and then chlorine, the noble gas before it is neon. So we start with neon, represents 10 electrons. So then we go to 3s2 and 3p5. And then sulfur, again, neon is 10 electrons. We have 3s2, 3p4. So that's how we use our abbreviated electron configurations. And if you're having trouble figuring out what comes next, you can go back to, let's see here. If I can get there we go. You can go back to this slide. So helium is at the top, and then when we come down, we go into 2s. Neon ends in 2p, so if neon is our noble gas, then we would come down to 3s. And then argon ends in 3p, so then we would come down to 4s. So that's kind of helpful to figure out which subshell comes next. Okay, so we said the noble gas notation helps us figuring out how many core electrons we have and how many valence electrons. But remember, if our highest shell number is represents our valence electrons, so we just have to look for the highest shell number. So in this example with silicon, 3 is the highest shell number, so those are going to be our valence, and anything below that is going to be our core electrons. So this gets a little tricky when we have D in the mix. So here, 4 is our highest shell number, so anything in shell 3 or lower is going to be our core electrons. So even though 4s and 4p have 3d between them, the 4 still represents those valence electrons. So let's do some of those examples. So we already did the electron configurations in problem 6. So we're going to use those for problem 7. So we're just going to do a few of them. So potassium, we've already done the electron configuration, and we know that the highest shell number is 4. So 4 is going to be our valence. So there was only 1 electron in 4. So we have 1 valence electron. So everything else is going to be our core electrons. So shell 1, 2, and 3 represent our core electrons, and that would be 18. Okay, and then iron we also did. So our valence is the highest shell number. So this one is one of those weird ones because we have D there. But our highest shell number is 4. So our valence is going to be 2. And then we're going to have 24 core electrons. So everything else is core. And then selenium we also did. So valence, our highest shell number is 4, and we have 6 in shell 4. So everything else is going to be our core, which was 30. Okay, so the nice thing about electron configurations is that elements in the same group have similar electron configurations. So you can see the ending for group 1, they all end in S1. So the only thing that's changing is their shell number. So as we go down the group, the shell number gets higher. So hydrogen is 1s1, lithium 2s1, sodium 3s1, potassium would be 4s1. So they have similar endings in their electron configurations. That's why they have similar properties. So we learned, I think back in chapter 5 maybe, we were talking about how Mendeleev grouped the elements in the periodic table. We said the groups had similar properties, and it's because of their electron configurations. So if they're in the same group, they have the same ending except for the shell number. As we go down the group, the shell gets higher.